Having seen the generalized heat conduction equation, now I am going to consider very important case in heat conduction chapter, that is heat generation inside a slab. Whenever there is a uniform heat generation is there inside a slab, let us find how do the temperature inside the slab change from location to location. That is, what is the temperature profile inside that slab. Let us try to understand how we can draw the temperature profile inside that slab, and after getting that temperature distribution inside the slab, you would be able to calculate the temperature within the slab at any particular location. So, next case what I am going to consider is heat generation inside a slab, wherein we will be getting the temperature distribution inside the slab, with the help of which we are able to calculate the temperature at any particular location inside the slab, and we will be able to plot graphically the temperature variation inside the slab, okay, with respect to location, point to point. Come on, let us see this very important case. This is so many cases, so many exams, so many years, there were many questions being asked on this heat generation inside a slab. I have considered a slab of thickness 2L. I have considered a slab of thickness 2L. This particular yellow color line I have shown is a midplane of the slab, center line or the midplane of the slab. The slab is of thickness 2L. The midplane of the slab I have considered as a reference line to measure the x coordinate. X is 0 at that midplane, that is right hand side section x will be plus L, left hand side at x will be minus L. There is uniform heat generation inside the slab of magnitude q dot. Q dot is the symbol for the heat generation, which is of uniform. Throughout the slab it is uniform. Every location inside the slab, every point inside the slab, heat generation is same, okay, at every location. Uniform means that. Uniform means same at every location. Uniform heat generation throughout the slab. It is uniform heat generation throughout. It is not that one point you are generating that heat. Everywhere you are generating, same amount we are generating throughout the slab. How that heat generation can be? Maybe because of electrical means, maybe because of nuclear fission or nuclear fission, or maybe there may be a chemical exothermic reaction. Heat can be generated inside the body by so many means, electrical, chemical or nuclear. So, but whatever the heat generation I am talking about, that is uniform throughout the slab, same amount of heat generation, everywhere there is heat generation, okay. So, this is x is the origin I have selected. X is equal to plus L on the right side, x is equal to minus L on the left hand side. K is the thermal conductivity of the material of the slab, which is assumed as constant. K is constant here, okay. Now, my objective is, every analysis should have the objective, right? Every heat transfer analysis, there must be objective. What is the main objective here? To get temperature distribution. What do you mean by temperature distribution? How do the temperature variation with respect to x? To get temperature distribution within the slab, that is temperature as a function of x. So, once I get the temperature as a function of x at any location inside the slab, now I would be able to calculate the temperature, and you would be able to plot the temperature profile also, okay. Any analysis, we should have the assumptions. considerations or assumptions. First and foremost assumption, which is very common assumption we make throughout the heat transfer subject, that is steady state heat transfer. That is, temperature is not a function of time. Temperature is not a function of time. Then many people will get a doubt here. We are generating heat uniformly throughout the slab. When the heat is being generated, how come the temperature remain constant with respect to the time when there is heat is being generated inside the body? Generally, that should result in the rise in temperature of the body. But we are assuming a steady state. For that, this is the situation. This is the energy balance. To maintain the steady state heat transfer conditions of the slab, whatever the heat generated in the entire slab must be convected either from one side of the slab or from both sides of the slab. Convection to fluid. Then only we are able to maintain the steady state heat transfer conditions, either from one side of the slab or from the both sides of the slab. Convection to the fluid. Please remember this boundary condition whenever there is heat generation inside any body, need not be slab. Whether there is a heat generation inside a slab or a cylinder or a sphere, the most important boundary condition we have to assume, you have to remember in mind is to maintain the steady state heat transfer conditions while generating heat. All the heat generated in the entire body must be convected either from one side of the must be convected from the surface of the body to the fluid. In this case, either from one side of the slab or from both sides of the slab. That is true for any shape of the body, need not be slab. Please keep remember that boundary condition, that if you are generating heat inside a body, whatever may be the shape of the body, if you want to maintain the steady state situations, all the heat generated in the entire body must be convected from the surface of the body to the fluid. Must be convected, should be given off. Then only we can maintain the steady state conditions. This is a very important boundary condition. I am writing here. To satisfy this steady state heat transfer conditions, must be convected to fluid. Fluid must be convected to fluid. The fluid temperature may be T infinity here. So that convection may happen either from one side of the slab or from both the sides. That is irrelevant. But whether it may happen that convection from both sides, or sometimes it may happen only from one side. Either from one side of the slab or from both the sides. To satisfy the steady state heat transfer conditions, all the heat generated in the body must be convected to fluid either from one side or from both the sides. That point you have to remember. Second assumption is one-dimensional heat conduction. That is, T is a function of X only. Number 3, uniform heat generation. Q dot is constant. And constant thermal conductivity, and K of the material is also constant. So these three are the assumptions we make. Three assumptions: steady state heat transfer, one-dimensional heat conduction, and uniform heat generation. Uniform heat generation means Q dot is not a function of X or Y or Z. Q dot is constant. Uniform means same at every location. And material property K is also a constant. And with these assumptions, I will get the temperature distribution by bringing in that generalized heat conduction equation. Dou square T by dou X square plus dou square T by dou y square plus dou square T by dou z square plus q dot by k is equal to 1 by alpha into dou T by dou tau. Many parameters in this equation will become 0. Why? You can see here. Temperature is not a function of time. When temperature is not a function of time, dou T by dou tau becomes 0. And it is one-dimensional conduction. Temperature is not a function of y, temperature is not a function of z, they become 0. Okay. So, you are left with only two terms. Now, we can remove this dou, I can write d. Instead of partial derivative, we can write a full derivative. That is d square T by dx square plus q dot by k is equal to 0. Implies d square T by dx square is equal to minus q dot by k. Integrating with respect to x, dt by dx first time I am bringing in the constant of integration C1, constant of integration C1. First time I am writing the constant of integration C. Q dot k by x plus constant of integration. After integrating, again integrating with respect to x, minus q dot by k into x square by 2 plus c1x plus c2. Because I already said it is a second order differential equation. Look at this, it is a second order differential equation. There obviously after integration we get two constants of integration C1 and C2. C1 and C2 are constants of integration because we did not write the limits of integration. In the earlier cases, wherever I have integrated, I have put the limits of integration, thereby I did not require the constants of integration. In the earlier cases where I did the integration, there was no need to write the constant of integration because we have written the limits of integration, different integral. Now, in this case, there is no limits of integration. Therefore, it is an indefinite integral. Therefore, we have to bring in the constants of integration. How to get them? From the boundary conditions. C1, C2 are constants of integration. Constants of integration that are to be obtained from boundary conditions. That are to be obtained from boundary conditions. Because we got the two constants of integration, we require two boundary conditions. One boundary condition I can clearly mark it here. One boundary condition is both sides of the slab are having the same temperature Tw. Both sides of the slab Tw, W refer to the wall. Please note that both sides of the slab are subjected to the same temperature Tw. W refer to the wall. So, when you can presume this, both sides of the slab, when you can presume this, when you can get this, Presume this was when you may achieve this. See, you are generating heat uniformly throughout the slab. Suppose that this side there is air, this side water is there. Obviously, water can cool the slab very quickly because water has got great convection, can provide a good convection coefficients. So, obviously, it can take the heat rapidly as compared to the other side because other side air is there. Obviously, air side temperature, this air side, the whatever the surface which is in contact with the air, it will be having the more temperature as compared to that side which is in contact with the water. Supposing both sides air, but one side you have the forced convection, wind is there, other side there is a free convection. So, obviously, the forced convection side will have the lower temperatures because air is taking the heat rapidly, both sides air, but that windy air is there, forced convection is there. Therefore, the temperatures will be relatively low on that side where there is a forced convection or wind is there. Other side it is a natural convection, still air. It is also taking, but it is taking slowly. The rate of convection heat transfer is lesser, maybe. Therefore, that is why the temperatures may be higher. But one thing is certain: whether you have the water air or air on the other side, whether the both sides air, whatever it is, the total heat generated in the entire body must be equal to the total heat convected from right side plus the total heat convected from the left side. Remember. If you are generating heat throughout the slab uniformly, if you want to maintain the steady state, the total heat generated should be equal to the heat convected from right side plus heat convected from the left side. So now because I am proposing the same temperature on both sides. To satisfy that, whatever the convection heat transfer that is happening right side with the H convection coefficient, same amount of heat should be convected from the left side also. That means that would be possible only if you have the same temperature on both sides. Only if you have the same temperature on the both sides, same fluid temperature with the same convection coefficient on both sides, same fluid temperature, same convection coefficient, and same fluid also should be there. That means with the same convection heat transfer coefficient, we should have the same H, we should have the same fluid temperature, and then only the same fluid temperature and same convection coefficient, then only you may achieve this TW, same on both sides. I repeat once again, if you want to see the same TW on both sides, the total heat generated is 50% should be convected from right side, 50% must be convected from the other side. Okay, for that we should have the same fluid with the at the same temperature with the same convection heat transfer coefficient H. One boundary condition is one special boundary condition, more correctly, right? One special, it may not be possible all the time. It may not be possible all the time. One special boundary condition is at x is equal to plus L and x is equal to minus L, that is both sides of the slab, T is equal to TW, same temperature. Okay, that is both sides we are seeing the same temperature, which is a very special boundary condition. When this will be possible, I am writing that chance also. When this will be possible? This can be possible only if both sides of the slab are subjected to the same fluid are subjected to same fluid at the same temperature with the same convection heat transfer coefficient H. Are subjected to the same fluid at the same temperature with the same convection heat transfer coefficient H. That is, out of the total heat generated, 50% heat is convected from right side and 50% heat convected from the left side. Actually, to satisfy this boundary condition, T is equal to TW at x is equal to plus L and x is equal to minus L, this C1 should be 0. The C1 value should be 0 to satisfy this particular boundary condition. Why? If you keep x is equal to plus L, you are getting some temperature, say some temperature. If you keep x is equal to minus L, you cannot get the same temperature because minus will come out. If you add one C1x, you will get one value. If you subtract C1x, you will get a different value. That means I don't want this x here. I don't want this x. That means this x will vanish only when C1 is equal to 0. If x is if x need top, I don't want the x there. If x is there, we cannot get the same temperature on both sides, because if you write plus L here, you get one value. You get to write x is equal to minus L, you will get a different temperature. Here no problem, because whether x is equal to plus L or minus L, square is always a positive, it doesn't matter. But the problem with x, so if you want to satisfy this boundary condition, x should not be there. For that will happen only when C1 is 0. To satisfy this boundary condition, C1 should be 0. Okay, C1 has vanished. Actually, please note that in case if both sides of the slab are at different temperatures, then C1 need not be 0 and it will not be 0. In case both sides of the slab are at different temperatures, C1 will not be 0. Mind that C1 will be 0 only when same temperature you are observing on both sides of the slab. Okay, I am continuing with this boundary condition, special boundary condition. The temperature of the slab is maximum when dt by dx is 0, because t is a function of x. Only when dt by dx is 0, the temperature of the slab is maximum. So look at that, where is the dt by dx? Dt by dx here. Okay, so I am substituting that dt by dx is equal to 0 here, and to get that location where the temperature is maximum. Okay, I am substituting that 0 is equal to minus q dot by k into x plus C1. C1 has already become 0. C1 already we made it 0. Because why C1 is 0? Why C1 is 0? Because you want to see the same temperature on both sides of the slab. Okay, so Q dot cannot be 0 because there is heat generation. K cannot be infinity. So only probability is x should be 0. Where is x0? If you look at the figure, where is x0? That is at the mid plane. This is the mid plane, center line, right? This is the mid plane. That is at the mid plane of the slab. That means we see the maximum temperature of the slab at the mid plane of the slab. We see the maximum temperature of this slab. That is, I am writing here. That is, we see maximum temperature of slab at its mid plane, conditions apply. When you can see that only if both sides of slab are at the same temperature. Only if both sides of slab are at same temperature. Only if both sides of the slab are at same temperature. In case if both sides of the slab are not at the same temperature, then C1 will not be 0. When C1 will not be 0, X will not be 0. Obviously, when X is not 0, then you may see the temperature, maximum temperature, you may see it on the left side or left hand side of the slab or on the right hand side of the slab. I repeat once again that statement that only when the both sides of the slab are at the same temperature, then only you are able to see the maximum temperature of the slab at the midplane. In case if both sides of the slab are at different temperatures, you may see the maximum temperature either this portion or in this portion. That converse is also true. Converse means what? In case if both sides of the slab are not at having the same temperature, then you will definitely not see the maximum temperature at the midplane. That maximum temperature might happen either in the right half or in the left half. Now I am continuing with this boundary condition, that is both sides are at the same temperature. Let the maximum temperature of this slab be T naught. Let the maximum temperature of this slab be T naught. That is at X is equal to 0 midplane. No, we are observing that the midplane. T is equal to T naught. I am denoting that maximum temperature of the slab with T naught. Now, if you substitute that boundary condition here when X is equal to 0, T is equal to T naught, what is that C2 value will become? T naught, because C1 has already become 0. At X is equal to 0, we are maximum temperature getting T naught will become C2. Therefore, if we substitute this boundary condition in that equation, T naught will become C2. We got both the constants of integration. One constant of integration C1 has become 0. The other constant of integration C2 has become the maximum temperature which you are observing at the midplane of the slab. So, we got the temperature distribution. Therefore, the temperature distribution within the slab is T is equal to C1 has already become 0, that C2 has become, that is, so this is the temperature distribution. This is the temperature distribution which is of parabolic type. This is parabolic temperature distribution. This happened to be a symmetric parabola, we can see here. This happened to be a symmetric parabola. Supposing if this is the midplane, you see the parabolic symmetric parabola. We see the symmetric parabola because we are observing the same temperature on both sides of the slab. At maximum temperature we are observing at the mid plane. At the mid plane we are having the, that is at x is equal to 0, mid plane we are observing the maximum temperature. It is a symmetric parabola. For the symmetric parabola to occur, what is the condition? Both sides must be at the same temperature. That means what is the requirement? What is the requirement? Both sides of the slab must be convecting the same heat. Both sides of the slab are convecting the same heat to the fluid. Both sides of the slab are convecting the same heat to the fluid. 50 total heat generated in the entire slab, 50% heat is convected from the right side, 50% heat is convected from the left side. Now if you put x is equal to plus L or minus L, if you put x is equal to plus L or minus L in this, at x is equal to plus L or the boundary condition, first boundary condition, if you substitute here, what is the temperature? We have assumed T is equal to TW. If you substitute that one here, you get T0 minus TW is equal to Q dot L square by 2K. Symmetric parabola means symmetric about the mid plane. Now if you divide this equation, if we call this as equation 1, this equation as 2, if you divide 1 with 2, you get a temperature distribution in a non-dimensional format. T0 minus T by T0 minus TW is equal to x by L whole square. It is also a temperature distribution in a non-dimensional format. Temperature distribution within slab in non-dimensional format or dimensionless format. Okay, but if you want to get this, so we'll look at this. If you want to get this maximum temperature, this is the T0 is the maximum temperature, right? If you want to get this maximum temperature which is observing at the, which you are seeing at the mid plane, we should require this TW, is it not? You want to get the T0 that is occurring at the mid plane, first of all we have to get the TW. How can you get the TW, the surface temperature? That can be, TW can be obtained from the energy balance for steady state. What is energy balance? For steady state conditions of the slab, the total heat generated in the entire slab should be equal to the heat convected from right side plus heat convected from the left side. Remember, whenever there is a heat generation inside any body, need not be slab, maybe cylinder or sphere, any case, if you want to get the total heat generated, if you want to get the surface temperature, whenever there is heat generation in any body, slab or a cylinder or a sphere, if you want to get the surface temperature of the body, the required energy balance boundary condition is, the total heat generated in the entire body must be equal to the total heat convected from the surface of the body. Please remember that boundary condition. Many times that may be asked, that was asked in the gate also. If you want to get the surface temperature whenever there is heat generation inside a body, the total heat generated in the entire body must be equal to the heat convected from the surface of the body. So now I am going to get that TW. To get TW, that is, what is the TW? That is surface temperature of slab, which is existing same on both sides. The energy balance for steady state. What is the energy balance for steady state conditions of the slab? Total heat generated in the entire slab is equal to total heat convected from both sides. From both sides of slab. Total heat generated in entire slab is equal to total heat convected. What is the total heat generated? Heat generated per unit volume is Q dot. What is the volume of this slab? Look at this. What is the volume of this slab? If A is the area of this slab, what is the volume? A into 2L. No, this is L, this is L. L into L plus L 2L. That is Q dot into A into 2L. That is the volume of this slab. Should be equal to the total heat convected. Whenever there is a convection, what is that law we always use? Newton's law of cooling. HA TW minus T infinity into 2. Because why I am writing 2? Because this is a heat convection from one side. Newton's law of cooling. Look at this. Look at this. HA delta T. See this. This is TW minus T infinity. H is the convection coefficient. A is the area of convection. This is the heat convection from one side will be HA delta T, temperature difference from the Newton's law of cooling. The same heat is convected from the left side also. Because we are proposing the same temperature on both sides, the total heat generated in entire slab should be equal to the heat convected from right plus heat convected from left. Because we are proposing the same temperature, this convection heat should be equal to the left hand side convection. That is why I multiplied with the 2. So you get cancelled, that A gets cancelled, 2 also will get cancelled. You get TW is equal to Q dot L by H plus T infinity. This is the side wall temperature, that which could be substituted to get this T naught. T naught, here. T naught is equal to, which you are seeing the T maximum. Where you are seeing this? That is at x is equal to 0, mid plane. From this, what is that? Here, from this equation, from equation 2, T naught is equal to TW plus Q dot L square by 2K. What is TW? That is Q dot L square by 2K plus Q dot L by H plus T infinity. What is the T infinity? Fluid temperature. Fluid temperature which is existing same on both sides. Fluid temperature on both sides is T infinity. This symbol we always give it for the fluid. H is the convection coefficient which is remaining same on both sides. L is the half of the thickness of the slab. This is the maximum temperature. This TW I have substituted here in this. This TW I have substituted here. I got the T naught or the T max. So now we got the temperature distribution. We got the temperature distribution inside the slab, which is a symmetric, where we see the maximum temperature at the midplane, where both sides are at the same. We know how to calculate the maximum temperature. This is half of the thickness L. Okay, K is the conductivity. H is the convection coefficient, which is same on both sides. T infinity is the fluid temperature, which is the same on both sides. H, whenever there is a H, what does it mean? H indicates what? Convection. Just like K indicates conduction, H signifies convection. H notifies convection, just like K notifies conduction. Symmetric. Okay, now this is a very special boundary condition. Special boundary condition in the sense heat generated inside their body, 50% left, 50% right convection. But this is very difficult to achieve practically, this special boundary condition. One extreme assumption, I can say this is some extreme assumption which may not be possible most of the occasions, because if you want to get this boundary condition, if you want to see this kind of a boundary condition, same fluid temperature, and same, the same fluid should be there, same convection should be coefficient must be there. Achieving this kind of a things may not be impossible, but generally we may not see that conditions. The other extreme assumption I am going to propose now. What is that? One end of the slab is perfectly insulated. I suppose that one end of the slab is completely insulated, perfectly insulated. That means there is no chance for convection from that side. And that means all the heat generated then should have to convect only from the one side, because that road is closed. It cannot convect from that side because that surface is insulated. So under that conditions, what will happen? Let us see now. Now I am proposing other extreme situation, that one end of the slab, one side of the slab rather, is perfectly insulated. The other extreme situation I am proposing here, is one side of the slab is perfectly insulated. One side of the slab is perfectly insulated. Because it is perfectly insulated, this side Q convection is 0. So all the heat generated must be convected this side only. Then the Q convection here should be total heat generated in slab to maintain steady state. This is for steady state, to maintain for steady state. Total heat generated should be equal to this side, all the heat. Because Q convection is 0, there is a Q convection is 0. When Q convection is 0, there can't be any Q conduction. Here the Q conduction is also should be equal to 0. When Q convection is 0 here, see at the left hand side surface, there cannot be any possibility of the heat storage there, because that surface has 0 mass. It cannot store, because if supposing there is Q conduction, if there is no Q convection there, that heat must be storing there. That there is no chance for that surface to store, because Q convection is 0, Q conduction also should be equal to 0. That means Q conduction is 0. That means that is, I can say, heat conducted at the insulated surface, heat conducted at the insulated surface should be equal to 0. Why? Since Why? Since no heat storage possible at the surface. That means heat convected at the surface should always be followed by the same heat. These two should be equal. Same heat conducted at the surface. Heat convected at the surface, I repeat once again, this is a very important surface boundary condition. Heat convected at the surface must be preceded by the same heat conducted at the surface. This conduction and this convection should have to be equal. This conduction and this convection should have to be equal because that surface has zero mass and it can't store any heat. Heat conducted should be equal to heat convected. These two should be equal, these two should be equal because we know that this is an insulation, no convection possible there because the surface is insulated. Q convection is 0, Q conducted also should be equal to the 0. That means heat conducted at the insulated surface is 0, that means minus Ka dt by dx is equal to 0 at the insulated surface. K cannot be 0, A cannot be 0. Therefore, dt by dx should be is equal to 0 at the insulated surface. That is T is maximum. That is T is maximum at the insulated surface. T is maximum at the end. So we can show it here that temperature profile also, how the temperature profile is there when the surface is insulated. This hatching shows the insulation. The temperature profile will be like this. Parabolic only, it is the maximum temperature. This is the parabolic only, but maximum temperature at the insulated surface. This is the maximum. This is insulation. So when one surface is insulated, this is when one surface is insulated like this, you see the maximum. There, of course, there is a uniform heat generation is there throughout. This parabolic kind of temperature profiles you see, only this parabolic temperature profiles you see whenever there is a heat generation inside a slab. This similar thing we will see in the heat generation inside a cylinder and heat generation inside a sphere also. So whenever there is a heat generation inside a slab, you remember that the temperature profile would be a parabolic temperature profile. Now I will consider another case. In case if both sides of the slab are at different temperatures, both sides of slab are at different temperatures, while generating heat in the slab, then in case if both sides of the slab are at different temperatures, then supposing if this is T1, you may see like this. Okay. This means T1 is greater than T2. Uniform heat generation is there. T1 is greater than T2. You see the maximum temperature on that in that half. Suppose this is the midplane. This is the midplane. Yellow color one is the midplane. You see in that part of the portion, in that half, where that one side of the slab is more greater. That side, if it is more, here T1 is greater than T2. Both sides convection is happening. Nothing is insulated. We have the convection this side. We have also has got the convection this side. We have the convection on both sides. We have the convection on both sides, but T1 is greater than T2. Then you see the maximum temperature in that side. In case supposing if both sides of the slab are different, but right side temperature is more than the left side temperature. In case if the right side temperature is more than the T2 is greater than T1, say for example, then you see the maximum temperature in the right half. This is the midplane. So I can say this is T2 is greater than T1 and there is uniform heat generation is happening. So we have shown you all the options. In case if both sides of the slab are at the same temperature, you see the maximum temperature at midplane. There is convection happening here. There is a convection, Q convection, nothing is insulated. There is also a Q convection here from the left side, but only thing is the temperatures are not equal. The right side temperature and the left hand side temperature, they are not equal. T2 is greater than T1. So this is possible, this is possible. So I had given you totally, supposing left side is insulated, left side surface is insulated, you are seeing the maximum temperature. If the right side is insulated, you see the maximum temperature there. So any option is possible. Supposing if the right hand side surface is insulated like this, you are generating heat, right side is insulated. Right side is insulated, then how will be the temperature profile? Then you see the like this. Maximum temperature you see on that surface where it is insulated. Parabolic only, all are parabolic. All the temperature profiles are parabolic. But this we can call it as the unsymmetric parabola. This is unsymmetric parabola. All are parabolas, but this is an unsymmetric parabola. This is also unsymmetric parabola. This is unsymmetric parabola. Symmetric parabola we will see only in case there is a uniform heat generation, in case both sides of the slab are at the same temperature. Under that condition only we see the symmetric parabola. This is right hand side is insulated here. This is insulation. No conduction there, no convection there. This is insulation. There is a convection here. So all possibilities are there. So we have done the heat generation inside a slab. But in all these cases, what is a common phenomenon? Uniform heat generation. Q dot is not a function of x, not a function of y, not a function of z, and thermal conductivity is also constant. But one thing is certain, in all these cases I have discussed above, for steady state, the total heat generated in the entire slab should be equal to the heat convected from right side plus heat convected from the left side of this slab. In all these cases, I can generalize that in all the above cases, for steady state of slab, for steady state conditions of slab, in all the above cases, total heat generated, this is the required boundary condition, total heat generated in entire slab should be equal to the heat convected from right side of the slab plus heat convected from left side of the slab. This is for steady state. Heat convected from left side of the slab. This is the energy balance. This is the energy balance. This equation only is called as energy balance for steady state. Heat convected from right side of the slab plus heat convected from left side of the slab. In case one side of the slab is insulated, that side there is no heat convected at all. Now we shall solve some previously asked questions. A composite wall is made up of two layers of thicknesses delta 1 and delta 2 having thermal conductivities K and 2K and equal surface areas normal to the direction of heat flow. To a composite wall is made up of two layers of thicknesses delta 1 unequal thicknesses delta 1 delta 2. Okay, this is K, this is 2K. This is the direction of heat flow. Composite slab, no heat generation mentioned. Please consider that heat generation only when it is mentioned in the problem. If there is no mention of heat generation, take it as 0. Outer surfaces of the composite wall are at 100 and 200. Which side 100, which side 200 is not given. This is, I am taking this as 100, this as 200. That means the direction of the heat flow will be from right to left. The heat transfer takes place at required surface term at the junction it is 150. At the junction it is 150. Right side from right to left, because heat always flow from high temperature to low temperature. So this one is 200, this one is 100. Just draw the thermal circuit, you get the answer. This is 200, this is 100, current is flowing from right to left. This is delta 1 by Ka, this is delta 2 by 2K into A. Current is like this. So the current is same. Series circuit, Q is equal to 200, this junction is 150, he has given 200 minus 150 divided by delta 2 by 2K into A is equal to 150 minus 100 divided by delta 1 into Ka. Ka gets cancelled. We know we can get delta. From this, we can easily get the delta 1 by delta 2. Very simple question. 200 of this is 50. This 2 will go 2 into 50, 100. 100 is equal to 50. Delta 1 into 100 is equal to delta 2 into 50. You will get delta 1 by delta 2. 6 kilojoules of conduction heat transfer has to take place in 10 minutes from one end to the other end of a metallic cylinder of 10 centimeter square cross sectional area. Area is 10 centimeter square and length is 1 meter and conductivity of the material is 100 watt per meter Kelvin. What is the heat transfer rate? What is the heat transfer rate? If this is T1, heat transfer rate is how much? 6 kilojoules. 6 into 1000. How much time? 10 minutes. 1 minute is 60 seconds. So, 10 times 100, that is heat transfer rate. 1000 by 100 is 10. 10 watt. 10 watt is the heat transfer rate. Q is equal to Ka delta T by B. Here the B is 1 meter. This is B here. That is given as 10 watts because 6 kilojoules means 6000 joules divided by 10 minutes it should happen. 10 into 60, that is 10 watts. 10 times you should get 10 into 10 is 100. 1000 by 100 it will be 10 watts. This is the rate of heat transfer. Write the Fourier law. Ka delta T. We require the delta T. What is that? K is given 100 into area is given as 10 centimeter square. 10 into 10 power minus 4 because you have to convert into the meter square divided by B is 1 meter is equal to 10. So you will get the delta T. Simple question. B is 1 meter. The thickness, thickness of the cylinder, the length of the cylinder itself is the thickness. Delta T is T1 minus T2. These are very simple questions. Q is equal to Ka delta T by B. Heat is conducted at the rate of 30, Q by A is given. 30 watt per meter square. Conductivity we don't know. Delta T is temperature difference is 10. The thickness is 0.1 meter. You will get the K in watt per meter Kelvin. Is also simple Fourier law. Q is equal to Ka delta T by B. K is a plane wall. K has been given 0.5. A plane wall of area 1 meter square. Temperature difference is 60. Thickness is 0.25. You will get the heat transfer rate in watt. Bulk modulus of elasticity. Bulk modulus has got the same units as that of pressure. Bulk modulus will be kilonewton per meter square or Newton per meter square. A is 2. A is 2. Thermal conductivity B is watt per meter Kelvin 5. Heat transfer coefficient C. Heat transfer coefficient is H, watt per meter square Kelvin 6. Heat flow rate, it is in watt 4. 2564. Answer is B. Very simple question. Two materials are given there. We can see the slopes are lesser here. K1 is definitely greater than K2. Since slope is lesser, slope is more. This could be done by a series circuit. It is a previous gate question only. First construct the thermal circuit. This is the thermal circuit. This resistance will be B by Ka. What is the area? Area of the conduction is always the area perpendicular to the direction of the heat flow. He has clearly mentioned that this dimension perpendicular to the plane of the figure is 1. He has clearly mentioned the depth of the slab is 1 meter. Okay, this depth of the slab is 1 meter. So, what is the area? 1 into 1, that is area will be 1 into 1. This is current Q. For this, B is 0.25. For this resistance, K is 0.10. What is the area? Area will become, this depth is 1 into 0.5. Area of the conduction is the area perpendicular to the direction of heat flow. See this, this is the current goes, current comes and current goes like this, parallelly. These two resistances are in parallel. So, what is the area perpendicular? This is 1 into 0.5, I written that. Then the area, this resistance will be 0.25 divided by K is 0.04, 1 into 0.5. If this resistance is R1, if this resistance is R2, 1 by R equivalent. First you merge these two parallel by using this formula, 1 by R1 plus 1 by R2. If this is R1, this is R2. Then the total resistance will be, if you call this as R3, R total will be R3 plus R equivalent. R equivalent will be shunting, the two parallel resistances you have to merge by using this formula. You will be getting 28.6. These two resistances are in parallel to this one series. For this area of conduction is different, for this area of conduction is different. Fourier law clearly says that area of conduction is a area perpendicular to the direction of heat flow. The area perpendicular to this direction of heat flow will be this dimension into this depth. Depth means perpendicular to the plane of the figure. He has given this depth as 1 meter according to the problem. Answer will be 28.6. Units will be Kelvin per watt. Thermal resistance. First you get this R equivalent, add that to this resistance. You will get the total resistance.